let us look at the flash memory. We can use exactly the same things in here also, but in the flash memory, you are kind of in a NAND flash memory, you actually have a string of devices connected to each other in NAND structure. So 16 or 32 cells may be connected as with one select transistor. And program BT, let us say, is greater than 0 and erase BT is less than 0. Interestingly, the source and drain region over here now do not need a contact. See, in the NOR flash, you need a contact for the drain where the bit line would connect and a contact for the source where the source line would connect. Over here, we have bit line select and let us say ground select signals. There are two regular MOSFETs that do not have the control gate and everything kind of mechanism there. And only they connect to source or they connect to the bit line. There is no requirement of contact in between the flash cells now. So the density of the NAND flash is much higher than that of the NOR flash. Is this thing clear?
Yes, sir, since we are not using the contact, then we can say that it is more denser.
Yeah.
But then how the operation will happen, sir? Can you?
Yeah, that will come to anyways.
Okay, sir.
So now look at it like this. You simply have word lines and there is no need for having any contact over here. So these gates can actually come much closer. So these gates can actually come much closer and you can have a denser memory cell. NAND flash is therefore multiple times denser than the NOR flash. Okay? In a NOR flash, you had one transistor per bit, whereas in a NAND flash, you have 18 transistors. The source select and the gate select signals are extra. So 18 transistors per 16 bits. This therefore is much denser. Is it okay? Clear?
Yes, sir.
So can you please explain once again how the gates are coming closer?
You do not need a contact in here now. See, in the NOR flash, there was a contact that was required at the drain. What contact was that for? Bit line. And then you also needed a source line to be run.
Yes, sir.
So over here, they're saying there is only one contact over here for the bit line and one contact over here for the ground. No other moving out of the, what do you say? So,
okay, sir, got it. Yeah.
Because you have lesser contacts, you can be much denser.
Okay, sir.
So this is how it appears in the kind of a layout where after every say poly you had a contact or a source line running in, and over here for the NAND, it's completely just a string of devices, no space for contacts.
Yes, sir.
So for the NOR flash, contact is what limits further scaling of area. NAND flash can actually scale down at the same pace as the poly to poly spacing scales down. At least that was what the initial thought was. And you see, this is how so many transistors this is how your NAND flash is denser. Okay. Another cross-sectional image where you see that different word lines simply go like this. There is a source line that connects to the source, and there is a drain line which connects to the bit line.
I doubt regarding the previous slide, sir. The final reason I'm not audible, sir.
I'm sorry, दोबारा से बोलो.
Sir, I'm audible.
Yeah, you are audible, but a little low on volume.
Sir, I wanted to know in the previous slide, the main reason for the NAND to be denser was the poly spacing.
So
I'm not convinced with the reason of the NAND to be more denser. Can you just highlight once more?
okay, because now let me repeat. See, in a NOR flash, you had a poly, you had a contact for the source, and you had a contact for bit line. Am I right?
Yes.
Then there would be another poly over here. So what is the spacing between two polys? Contact plus 2 COPO spacing. So
Okay, sir. Okay.
one COPO here, one COPO here, and the contact width. Whereas if there was no contacting in between,
As in the case of NAND.
yes, as is the case of NAND, then the two cells can actually be much closer. You just need
Because sir, you also mentioned in one slide the number of transistor per bit required in the NAND or more.
yes. Over here,
Yes,
we said if we're storing 16 transistors, we have 16 transistors in this string. There are 2 extra transistors for the gate and the bit line select, for the ground and bit line select.
Okay.
And
Despite
remaining,
having these 2 extra transistors, NAND are denser because of that contacts are not there in between them.
yeah.
Okay. No doubt. Thank you.
Okay. So what are the scaling challenges linked to a NAND flash? So I'm writing something, you should actually ask details from Kalyan in the next class. First is performance. See, as you scale down, the currents would reduce. Second is VT distribution. As you scale down, because the floating gate is now smaller, mismatches will happen more prominently, and there will be a challenge of VT distribution over there. And then since we are applying very high voltages, we were talking about plus 10, minus 5, or minus 10 and 6 to 8 volts on the bulk, talking about very high voltages put across the control gate to the bulk part. So with these high voltages, there can be a lot of issues on reliability. So in NAND flash or even in NOR flash, reliability is something that you should always be extremely careful about. So again, when you want to program, what do? So in a NAND flash for programming, so in a NOR flash, what did we say programming with?
Hot carrier and
HCI.
yes.
But in a NAND flash, we actually do this also with FN tunneling. We simply create an inversion layer here, 0 volt on the bulk and 18 to 20 volts on the control gate. Electrons simply get the energy to jump into the float gate. If you want to erase, you simply change the connection. 0 goes on to the control gate and 18 to 20 volts, that is something of similar order, going on to the bulk. So all the electrons are thrown out from the float gate into the bulk again.
ऐसा ऐसे तो हम फिर नॉर में भी
ऐसे तो हम
सर नॉर में भी कर सकते थे हम, जिस तरीके से रीड और राइट कर रहे हैं।
yeah, but FN tunneling is much slower than HCI ना.
ओके, तो हमने हॉट कैरियर उस बार प्रोग्रामिंग के लिए वो यूज किया और ओके।
हाँ हाँ. Okay. So now it appears okay at a cell level, but you being memory designers, you also have to see what happens to the cells in the same row which are not to be selected. So आपने कहा I want to program, let us say, this particular cell. Huh? So its word line would go to 18 volts, but the same word line is going to so many other columns also. Huh? So how do you prevent write in other columns? How do you prevent write into the adjacent ones? You say that I will apply a different voltage on V pass, and a different voltage on the bit line. If you apply a different voltage on the bit line, what happens?
The charges are conserved in the other column.
When we apply this 8 volts over here, we in a way kind of ensure that the bit lines which or the source and drain which were kind of left floating are not really floating there then. They have a distinct voltage on them, and because of that, what happens? This 8 volts, so look at it like this. This transistor, the gate is at 10 volts, bit line is at 8 volts. What happens to this internal node over here? What would appear here? If the VT of this device is 2 volts, what will appear on this node?
8 only.
8 volts. So this 8 volts will actually, you will see, pass to this last device. Now, when the 8 volt is there on its source and drain, what happens? You want to apply HCI. But now you cannot apply HCI. Why? Because 8 volt has got transmitted over here until everything, and therefore the kinetic energy or the inversion layer that is formed will not have that kind of a thing happening. Is that okay?
Yes, sir.
And you could actually, so okay, for the flash memory, there is this one important figure of merit, which is like this figure of merit, which is like what is the ratio of gate coupling? What is the capacitance of the gate versus total capacitance? Okay? That needs to be taken care of. Now that was one scheme where we had to apply, now how many voltages are we talking about? 0 volts, 8 volts, 10 volts, and 18 volts. 4 voltages we're talking about. It means 4 different voltage regulators. Can I do something else? So there was this paper, a very old one at that, which talked about self-boosted flash. So what happens there? First of all, BL1 recharges all transistors to VDD minus VT. And if I put this at VDD, then BL1 will precharge everything to VDD minus VT. Everywhere it will become VDD minus VT. Am I right?
Yes, sir.
Then SSL goes off. What happens? All the channels, all the channels of all the transistors on BL1 become floating. Huh?
Yes, sir.
So, in a way, you used VDD only. You reduced the supply voltage there, huh? Instead of using a different VDD, and with some constraints, you are actually ensuring that this particular cell is not programmed. That this VDD is such that you do not program this. Is that okay?
सर ये वाला पार्ट नहीं आया समझ में।
क्या नहीं आया बताओ?
सर जैसे हम बोल रहे हैं कि वर्ड लाइन अगर हमारा 18 वोल्ट है तो सारे पैरेलल उसमें भी जाएगा, और आपने कहा कि बिट लाइन का वोल्टेज हम चेंज करके उनको प्रिवेंट कर देंगे कि उनमें डेटा करप्ट नहीं हो हमारा। तो
So let us look at it again.
यस
हमने पहले यहाँ पे VDD रखा था. We had kept VDD here and we are taking VDD to 0 when I want to write into this particular cell.
यस सर।
So when it was VDD, what was happening? At all these places, VDD minus VT must have got transmitted.
यस सर।
Not exactly VDD minus VT.
VDD
V pass, which is 10 volts minus VT.
यस सर। यस सर।
Huh? If VDD is less than that, then entire VDD would get transmitted. If it is more than that, then that little part would, then VDD minus VT will get transmitted.
यस सर।
Okay. So what happens? You taken this to 0, then as soon as you take this to 0, it is 0 everywhere. If it is 0
Yes.
everywhere, what happens? FN tunneling starts.
Okay.
Huh? Over here, that doesn't start because over here it is VDD minus VT.
अच्छा। Okay, okay, sir.
You not put the device in inversion region at all.
Yes, sir. Yes, sir.
So the programmation will not happen.
Okay, okay, sir.
Okay. Any further questions on this? Okay. So then if you look at the timings, if we start to look at the timings, then chip enable is low. It means your chip is active. Chip enable low. Chip enable bar is low. So your cell is active. Then address latch, column latch, everything, these are coming. Command latch, address latch are coming. So when the command latch comes, your IOs, you start to latch the command. When the address latch comes, you start to latch the address of the column and then in subsequent cycle of the row. Okay? And then you wait for data to be transferred for this column and for this row. Okay? And you do a data out. Is this clear? Okay, let me remove mine and show the. So this is the first phase, the command phase, then we have the address phase, then the data transfer phase. And once the data transfer has completed, you kind of say, okay, we will read out. This, though it has been shown to be a small bit, is actually a long phase. Okay? Now, when I want to program, what do I need to do? I again need to give a command. I need to give a column address and the row addresses. And then I start to send my data that I want to program in the memory. Okay?
Yes.
So we are able to, okay, so there is also, would you say, a counter or something which tells us that programmation is completed or not. Once it is completed, we start the next operation there. Okay. So now let's look at if we were to design a 1 gigabit flash memory, how would we organize it? So first thing is that 1 gigabit thing will be separated into two banks of 5 and 2 megabits, let us say. And in each bank, there will be blocks. What is a block? Suppose your memory cell had 32 cells in it. So the block will have 32 cells. And the block would have 32 words. Okay. So this is 32 then. Each block, there are 32 words. All cells on one word line form what is called a page. All of them will get programmed together. At any given point of time, when you select, say, one word line at 18 millivolts to program, all the cells, all the transistors on that particular row would get selected and programmed all at once. Is this clear? Now, why do you think over here we've added 32 bits? Over here also 32 bits. Why? Why are these 32 bits extra bits there?
Word line cells all are programmed together. Is it due to that?
The sense amplifier is also connected to them. You heard about error correction codes?
Yeah, just heard about.
Huh?
Just suno.
When I spoke, you got to know. Huh? Or you knew about it earlier?
Just know the name and see.
You just know the name. Okay. So error correction codes are used so that if there is some error that is script and either at writing or during read from a particular digital circuit, by storing the codes there, I can actually decipher what the error was. First, I can first detect that there is an error, and then decipher what the error was and correct the content of the memory. This is extremely necessary for flash. There was a point in time it was also extremely necessary for, what do you say, DRAMs. It adds error resilience in the presence of noise. So you will see that error correction is used widely. Then this set of 32 pages is called one block. Okay. Now, when you erase the memory, so when you program row by row. So you program every page in one go. But when you erase the memory, you erase the entire block.
So that means that particular row in every page, erasing the entire block.
Every row, yeah. So all the 32 rows, 32 cells are part of the block, and not just 32 cells. All the rows of those, all the 32 rows of that NAND cell, if the NAND cell has 32 bits, are a part of the page.
Okay, sir.
What would happen if you increase the page size? What would happen if you increase the page size? सॉफ्टवेयर टर्म्स में और इधर भी? हेलो, so as you increase the page size, as I said, the entire page would be deleted. As you increase the page size, your actually line length, the data that you're fetching from the main memory, from this flash into the main memory or elsewhere, increases. So the delay would increase, but the line length is essentially increasing.
Sir, would that also mean lesser number of bits will be required for error correction?
Why would you say that?
Sir, what does it depend on? The number of bits in error correction? Is that the size of the word?
Yes, the length of the word. For example, if the word is 32-bit wide, you will need for a SecDead code 5 error correction bits.
So it's like parity generation, something like that.
Parity is always 1 bit.
Okay.
But error correction code generation is dependent on, what do you say, how many bits your database has.
Okay, sir.
So we already saw the sense latches and the data as is. And this is how my one logical page is broken into 2 physical pages. So now what we are saying is that there are 8K plus 256. 8K plus 256 bits that are being read on the left side and same bits that are being read on the right side or written from the left and right side. So over here, if I say that this is my flash memory, 125 millimeter square, 1 gigabit flash memory, then there are bit lines that are running like this. Over here, in every block, how many word lines do I have? 32. And there are 1024 blocks. So there are 32K word lines in total.